Swayam Prabha. Digital India. Educated India.
So let us assume by induction that if it's a complete graph, all are simplicial vertices anyway, that none of them are non-adjacent. Otherwise, let's assume that there is two non-adjacent simplicial vertices. Now take a chordal graph and first ask, is the n vertex chordal graph, given n vertex chordal graph, a complete graph? Is it Kn? If it is Kn, then nothing to prove, we know that. If it is not Kn, there is at least one edge missing. There are two vertices which can be separated from each other. So let's say if there are two vertices which can be separated from each other, that means this edge is missing. Then that means there are some separator, right, which can separate this from this. Then there is a minimal separator also. Let's say this is the minimal separator, right? Let's say this is the minimal separator. Now this is a clique, right? Because it's a minimal separator, that has to be a clique. Because for chordal graphs, the minimal separators are cliques. Now we can look at this part. Maybe let me use a highlight. This part. That means separator and this side. And you look at this part. Separator and the other side, okay? This part. But in this part, I can apply my theorem, my induction hypothesis. If this part was completely a clique, then all the vertices are simplicial there, right? Because if including the separator and this entire thing, if this was complete a clique, and then any vertex could be done. You can always take one vertex somewhere here, which is a simplicial vertex, and look for a simplicial vertex from the other side of the separator. But otherwise what will happen is so what I mean is, so I can apply the induction hypothesis on one side. So that means there are two simplicial vertices. So I put two simplicial vertices. Similarly, on this side, there are two simplicial vertices, right? Yeah, let me write like this. This is 2 here, and these dots are 2 on the other side. Now you see, these two simplicial vertices are, suppose one of this star is here on the, not part of the minimal separator, on the other side, on the left side, and the other is on the right side. Then we got two simplicial vertices anyway, right? Because this simplicial vertex will remain simplicial vertex even if this part comes, because it's beyond the minimal separator, because it cannot have any neighbor on the other side. So its simplicial status will still be valid. Similarly, if this is on the completely on the right side of the minimal separator, even if we attach this will remain simplicial, right? So these two will be the candidate simplicial vertices, because this and this are non-adjacent, and also because they were simplicial in the original, in the smaller graphs, they are also simplicial here, because just attaching them together will not violate the simplicial property of those vertices, because whatever we are adding are not going to be neighbors of it. But then the problem is, if we don't get one here and one here, one on completely on the left side and one on the completely, but then there should be two, right? That means both should be, say when I consider the two simplicial vertices on this part, can both be here inside the minimal separator? No, why? Because they have to be non-adjacent, but they are all adjacent inside this thing. So one has to be here, right? We'll get. Similarly, one has to be here. Both cannot be in the minimal separator. At least one should be. Those two will make this thing. So that means we are able to get two simplicial vertices, right? This will this is not just one, two simplicial vertices are there, and they are non-adjacent as long as it is the caudal graph is not a complete graph. This is one thing which we are able to guess. Okay, now what I do is, so we have seen that. So what all things we have done today? So we define caudal graph, and then we proved that all minimal separators of caudal graphs induce complete graphs, and then we defined the concept of simplicial vertices, and then we showed how the previous lemma can be used to prove that there exists two simplicial vertices in caudal graphs. As long as it's not a complete graph, we will get two of them which are non-adjacent, right? So a single vertex is also a caudal graph, but then there is only one, it's a complete graph also. We are not claiming anything about the complete graph, right? And then we also showed that once we get, once we prove that there exists a simplicial vertex, then we can define the perfect elimination ordering by sequentially eliminating simplicial vertices, right? Such that with respect to the remaining graph, one vertex is always simplicial, right? And the most useful thing is that thing, perfect elimination ordering. Why is it useful? Because it helps us to find out like coloring strategies, or optimal coloring, or if you want to find what's the maximum clique. All these things can be done using perfect. So for instance, if I want to find a vertex coloring of proper vertex coloring of the caudal graph, which is optimal. Optimal means using minimum number of colors. Optimal color. So the using minimum number of colors, we want to color the vertex. So what would be a strategy? Can anybody tell me what would be using perfect elimination ordering? I am claiming that this can be achieved. Can you tell me what should I do? It's a easiest strategy, namely the greedy strategy, right? So what I do is I order the vertex set V1, V2, V3, so Vn. This is a perfect elimination ordering. V1b is the simplicial vertex, and V2 is a simplicial vertex in the graph induced on this part, and V3 will be a simplicial vertex in the graph induced on this part, and so on. Vi will be a simplicial vertex in the graph induced on this part, right? Now I start coloring from this end, okay, the other end of the perfect elimination. So that means this will get a color first. So this vertex, that Vn, namely this Vn, will get a color first. I can give a black color to that, right? Next, what will I take? I'll take Vn minus 1. Say maybe this is Vn minus 1. Vn minus, what is the property of the Vn minus 1? Yeah, if at all it is attached to this, yeah, no problem. We have to use a different color now, right? Anyway, it's unavoidable. And Vn minus 2 I will take. If it is like this, I can use the same color as this, right? So it should have been nice to get colors very easily, but unfortunately to get a color here, I would think better I don't need a color. 1, 2, 1. Right. Okay. So this will be the strategy. But it's possible that I can have this. Suppose this edge was there, right? Then I have to take a new color. It's required, right? It's not that I am unnecessarily doing it. It's required. Now look at Vn minus 3 now, third one. So I take a situation where, yeah, suppose So this is the thing. Now so suppose this was the situation. Then I see 3 here, 1 here. What should I give here? 2. Suppose I have this edge also. What should I give? Should I give 4? So you may wonder why I am giving 4 here. Maybe I can do with 1 less color, right? But the good thing is that if I am forced to give a 4 here, that is because I am seeing 1, 2, 3, all the colors which I cannot use on my neighborhood, right? So am I forced to take a new color? Yes, I am forced to, because the neighborhood is actually forming a clique, right? And with this vertex, it is 1 more than the number of colors I am seeing. The clique size is 1 more than the number of colors I am seeing in the neighborhood. So I have to use 1 more color. I hope you understood the point, no? Because usually when you do a greedy coloring, this is not true. So you just give a color to a vertex and give another color to the ith vertex. When you look at the neighborhood, you see certain colors and you give this vertex the minimum available color. Sometimes all the already used colors are appearing in the neighborhood. Then you are forced to use the new color. But you cannot be sure that you are doing the correct thing. Maybe you did something wrong in the neighborhood. Maybe your neighborhood you colored wrongly. Maybe your sequence of coloring you are doing up to now was not optimal, because when we came, if we had come up with some other coloring with the same set of colors but different pattern, probably you could have done better. But here you cannot. Why? Because in the neighborhood you see a clique, right? And whatever you see in the neighborhood is all different colors, because it's a clique anyway, right? They don't repeat at all. And with this vertex, it's a bigger clique, and because this clique is that many colors are required in the graph to color, right? And therefore it is not possible to do better than that. So at every stage you are using only those number of colors which are essentially needed. You can go about doing this greedy coloring without any prick of conscience. Why? Because usually when you do the greedy coloring, you are worried, oh, am I overdoing it? I mean, using a color which is not really necessary. Did I do till now, was it correct? Now it's a local thing. We don't have to worry whether you did it correct or not. You know that you're not using a color which is not really necessary. Finally, it's necessary, because you have a proof that this many colors are required when you are using a new color, right? Whenever you are using the new color, you have a proof just in front of you that this many colors are required, because you are seeing the clique of that number on that many number of vertices in front of you, including yourself, right? So therefore, by the time you reach V1, you have colored all the vertices, and every time you use the new color, you knew that optimal coloring will require that many colors, right? And you see, you have colored using the number of colors equal to the clique, biggest clique, right? Clique number is equal to what here? Yeah, so this is a perfect graph, right? Omega is equal to chi here. That's the chi perfection. Not only for the graph, also for all the induced subgraphs, because all the induced subgraphs are Chordal graphs again, right? By hereditary property. As I told you, if a graph does not have any chordless cycle of length 4 or more, then no induced cycle subgraph also cannot have a cycle of length 4 or more, right? Therefore, chordal graphs are, any induced subgraph of a chordal graph is again a chordal graph, and it follows that chi equal to omega here. And have we proved that chi equal to omega here? Because we have proved that the number of colors we use to color is equal to some clique, right? Is it the biggest clique? No, there cannot be a bigger clique in the graph. Why? Because suppose there was a bigger clique, you will not manage with this many colors, right? Because the number of colors required to color the graph has to be at least the number of vertices in the biggest clique. So if you have managed to color the graph with this many colors, and that is the maximum clique, it cannot be more than that, right? The point is that you manage with exactly the number of colors in the number of vertices in the maximum clique, right? The number of colors used is equal to that, and that was the best possible you did. No, but the neighbors are not colored at that time, right? When V1, you are giving color to the V1, and your neighbors of V1 are not yet colored, right? Because V1 is the first one to get colored. And that information is irrelevant to you right now, because they are not even colored. And suppose you are coloring the ith vertex. So what is already colored according to your strategy is V1, V2, Vi minus 1. But the neighbors of Vi, the neighbors of Vi are two types. One is the higher numbered neighbors, so we can call it NH of Vi. That means this can be Vi plus 10 or Vi plus 101, Vi plus something 21, right? The bigger numbers. And here this is Vi minus 2, Vi minus 33, something, right? Smaller numbers. So according to your strategy, all these vertices are colored by the time this. According to my strategy, all these vertices are colored. All these vertices are colored by the time this is to be colored. But according to your strategy, the Vi looks at the already colored vertices. They don't have any structure. They can be anything, because they may not form a clique and all, right? Because simplicial vertex, Vi is a simplicial vertex in this part, not in this part, right? Understood? See, because V1 was a simplicial vertex with respect to the entire graph. Now when you removed V1, you got V2, which is a simplicial vertex with respect to the graph on V2, V3, Vn, except Vn, without V1. If V1 is there, that V2 may not be a simplicial vertex, right? Okay. So now we have covered Chordal graphs. I think this much is enough for Chordal graphs for just a quick introduction. And let's, because 15 minutes are there, let's consider a very important special class of Chordal graphs, namely interval graphs. Interval graphs. What are interval graphs? Interval graphs are the intersection graphs of intervals on the real line. Okay. What are the when I say intersection graph, what do I mean? Have you heard about intersection graphs? So in general, we can tell like this. Suppose you have a universe, it's a set system notation, universe of U, and then you are given some subsets of U, S1, S2, some Sn. This is a family of subsets of the universe U. And now we can, given this set system, we can construct a graph out of this. It's called the intersection graph of this set system, this family of sets. How will you do that? So you introduce n vertices in the graph. So this you can call 1, 2, 3 up to n. and 1 correspond to S1, right? 2 correspond to S2 and so on. Now when do I put an edge between I and J? Yeah, when Si intersection Sj is non-empty. If there is something common in Si and Sj, then we put an edge between them. Otherwise, we don't put an edge between them. This is a intersection graph model, right? So, given any sets, family of subsets of a universe, we can construct an intersection graph. Usually, when we define like this, we ask, given a graph, can it be the intersection graph of some family of some universe, right? Some family of some subsets of some universe and all. But that is not very interesting question, because you know that any graph, this you might have read in any graph theory introductory chapter of most graph theory textbooks. That means any graph is the intersection graph of some family of subsets of some universe. Namely, if you consider the edge set as the universe, you take U as the edge set of the graph. Set of edges, that means I can write it as E1, E2, Em, where if there are M edges, right? And then for each vertex, then you can assign a set SV, namely say EI1, EI2, EIK, where E1, EI1, EI2, EIK are the edges incident on vertex V. I mean those edges which V sees, right? And now can you see that with this set of family of sets, and if you take the intersection graph from this thing, you get back the original graph from where we started? Do you understand what I am telling? See, what I took is the I'm given a graph. I am claiming that this graph can be represented as the intersection graph of some family of subsets. So when I say family of subsets, I should have a universe first, right? That I am saying that take the universe as the edge set of this graph, given graph. E1, E2, this one. And then I have to construct a subset of this universe corresponding to each vertex. So that's what I wrote as SV. So what should be the subset corresponding to SV? All the edges incident on V, right? So for instance, if this is the vertex V, this edges will be the subset, as if this is a basket or something, you can assume. So you are putting the sticks in that, right? So you say that your universe is those sticks which are the edges of the graph, and then each vertex I will imagine that it's some basket which is holding those sticks, right? Now do you see that when I take the intersection graph from this thing, so the corresponding to each vertex I get this basket only, right? Now when do two vertices have an edge between them? When the corresponding baskets have a common stick, that is when they had an edge between them, right? This it's a way of telling it back. So therefore that is not so interesting, but when it is interesting, it becomes interesting is this when we put some restrictions on the universe and the set of subsets we are using, right? For instance, we can make the universe as the real line, right? So then the subsets allowed to be see this S1, S2, etc. They are only intervals on the real line. Say let's say closed intervals on the real line. We can also use open intervals and all, but that's not really necessary. Closed intervals on the real line, right? Closed intervals on the real line. Now, given a collection of closed intervals on the real line, you can construct a graph for that, right? Whenever they intersect, put an edge between them. If they don't intersect, don't put an edge between them. This will be called an interval graph corresponding to that set of family of intervals, right? Interval graph. Now the reverse question, the question we ask usually is, okay, given a graph G, can I find an interval representation? Means, can I find a collection of intervals, one interval for one vertex, right? Associate an interval to a vertex, such that whenever there is an edge between two vertices, those intervals intersect. And whenever there is no edge between those two vertices, the intervals do not intersect. So that's the interval representation. That means this graph is the interval graph of those set of intervals, right? Is that always possible? In the earlier case, I told that I can always do, like with arbitrary sets and all, I can always do. But then with the intervals, it's not always possible. Can you guess some example of a graph, some graph for which an interval representation is not possible? C4 is a famous example. Why for C4 we cannot get an interval representation? That's possibly because C4 is like this, right? Yeah, C4 is like this. So 1, 2, 3, 4. Now let this be the first interval for the first vertex. Second vertex, I can put something like this, say. There are many possibilities. I could have put it containing this point, or I could have put it containing this point, or I could have put it something like this, right, inside. So let's take this decision. So if I put it like this, and the third vertex, when I put, this is 2, when I put the third vertex, I should make sure that it does not intersect with 1, but it should intersect with 2. That means I can only put it starting from somewhere here. I can put it inside, but I have to take it out, right? 3. But then how will I put 4? 4 is like it should intersect with 1 also, 3 also, but it should not intersect with 2. So this portion, it should intersect somewhere here, it should intersect somewhere here, but right? But how do I manage to put that interval without intersecting with this thing, right? So you will argue that no, you have to consider many other cases. Yes, consider it, but you try to prove that C4 does not have a interval representation. It's not very difficult. Just try to come up with a neat proof of this, right? Yes. So C4 cannot have an interval representation. So there are graphs which cannot have interval representation. So all graphs are not interval graphs, right? But C4 is familiar to us also anyway, right? So that was the defining graph for caudal graphs, no? The caudal graphs cannot have C4 as an induced subgraph. So here we are telling interval graph, C4s are not interval graphs. That also means that in an interval graph we cannot have C4 as an induced subgraph, because if in an interval graph C4 is an induced subgraph, we could have discarded all other vertices and got an interval representation for C4 there, right? Because any induced subgraph of an interval graph has to be an interval graph, because at least for those set of vertices, whichever interval we gave would have worked even when other vertices are not there, right? So C4 is not present in interval graph also. What is the conclusion? Conclusion is that all interval graphs are caudal. All interval graphs are caudal. But then you will ask me, are there caudal graphs which are not interval graphs. Is it possible that caudal graphs are essentially interval graphs? Are there caudal graphs which are not interval graphs? Can you think of some caudal graphs which is... See, one thing which you can notice is all trees are caudal graphs. Why are trees caudal graphs? After all, they don't have cycles, then there is no question of induced force cycle, right? So, by definition, they are caudal. So, but are all trees interval graphs? So, can you construct some tree which is not an interval graph? Can you think of some tree which is is a star an interval graph? Star means one vertex and this one, central vertex. Is this an interval graph? Can anyone come up with an interval representation of this one? Very good, something like this, see? This is the central, this long line is the central vertex and the leaves become the small intervals, right? So this is a star graph. But then can you construct a tree now which is not an interval graph? For instance, can you put these things as interval graph? So that means I am just extending them. No. So yeah, you have to convince yourself that it's not possible, right? Because say at least some of them should be, some of these things should be something which is inside it, which does not have any extension outside of the big line. And then if this has to, the other vertex, so this has to be an adjacent to this, as means I have to put something here, but then it will also be intersecting with this, right? So there are trees which are not interval graphs. So therefore, all caudal graphs cannot be interval graphs, but all interval graphs are caudal graphs, right? So now, let's say whatever is told for caudal graphs is valid for interval graphs also, but interval graphs do have more properties.